So electrons are going to be moving towards a positive charge. I think about just charges, and so I'm going to have an away from negative charges. So my field in the wire, right, if the electrons are moving this way towards positive, this would be negative. So I know that my field inside is going to be pointing to the right. Now what about current though? When we talk about electrons, when we talk about current, we think they're the same, but actually conventional current is defined in the opposite direction as electron current. So we can see here if my electrons, they're flowing, so if I look at this, this is a symbol for a battery, and this would be the positive terminal of the battery, and this would be the negative terminal of the battery. And electrons are going to want to flow away from the negative, so they're going to be flowing this way. And but if I talk about conventional current, when you're talking about current, you're talking about conventional current, and that's always opposite of the electron flow. So that's something you're just going to need to memorize. So the surface charges in a conductor is what causes like instantaneous electric field to be set up in this wire. And so what happens is I have an electric field, and the electric field is pushing electrons through the wire. And so I have this buildup of electrons on the corners of the wire, and that buildup, the positive charge is pushed because the electrons are moving through. It's pushing the positive charges here, and because there's a buildup of positive charges here, it causes my my electric field to turn away towards these charges and head along the direction of the wire. So the field itself is creating the buildup of charges to cause the electric field to run parallel to the wire. The resistance of a conducting object, right, is given by delta phi, so the change in potential over the current. And the unit of resistance is the ohm, and that is drawn as with a symbol that looks like that. And so Ohm's law is pretty important, and that's because we can use Ohm's law if we know the resistance of a resistor and we know, say, the voltage, then we can calculate the current, and vice versa. If I know what the current is and I know what the resistance is, I can calculate voltage. So as long as I know two of these variables, if I know the value of two of these variables, I can solve for the other. And so that makes it very convenient. And so we can use Ohm's law with resistors. We see here that the current is proportional to the voltage, as well as the resistance is proportional to the voltage. We can see that that when a material is ohmic, it means that the relationship is linear between current and voltage. We can see here this is linear. When we have a non-ohmic device, then we don't have this linear relationship. We can see here we have some kind of a power law relationship between I and V. Looks like maybe a squared or an exponential. So for ohmic devices, we want this linear relationship, and then we're able to use Ohm's law for these calculations. Power is dissipated in a conductor, and it's the rate at which electrostatic potential is converted to thermal energy. So we have power is equal to I times delta phi. So we have I, the current, times the potential. And so you can write it as P equals I squared R, right? Because delta phi is equal to IR, so it would be I squared R. Then I can also substitute in IR here, and I squared R squared would be delta phi squared, and then divided by R. So depending on which variables we know, we can solve for the power. And so the units of power are energy per time, so joules per second. Okay, this graph is talking about discharging a capacitor. And so what happens with a capacitor is it's put in series with a battery. And so when it's put in series with a battery, the charge starts to build up because the battery is pushing charge over to onto the capacitor, and it's building up on the positive plate of the capacitor. And then what we can do is we can disconnect that capacitor from a battery and hook it up to a resistor or a light bulb or something like that, and that will cause the current to flow in the other direction back and through the device, and it'll provide power for a very short time. And so you can characterize how long that time is using something called a time constant. And so we have the potential difference Vc at any time t is given by a and then exponent to the negative t over Rc. And so what we have here is we'll look at the voltage versus time. And I can see that my time is given in increments of Rc. So what that means is if my time is equal to 0, then I have e to the 0 would equal 1, right? E to the 0 equals 1, so my voltage would equal A, so that's the max value. And so here we have the max value is 9. When the time, t, is equal to a multiple of Rc, so let's say time is equal to 1 Rc, so here, when I say e to the negative, now if I plug in t is equal to Rc, then I have e to the negative 1. And e to the negative 1 is 0.37, and so that's 37% of the original max value, so original value of 9. So that's why I get 3.3 here, and so on. I can always express t in terms in multiples of Rc. So if I say t is equal to 2 Rc, then I get e to the minus 2, and so then I end up e to the minus 2 is 0.14, and so that 0.14 times my 9 gives me 1.2. So that's how you're able to figure out the time in terms of the time of the resistance and the capacitance, and what kind of voltage I can expect, and the shape of this curve is represented by that equation. So just to go into that a little bit more, so I have, in this example, I have my A is equal to 9 volts, so I wrote a 9 here. And then e to the negative t Rc, I can write that as negative x, so just this t over Rc is equal to x. And now if I have e to the negative x, that's the same thing as writing 1 over e to the x. And remember that e is equal to 2.7 something, I think. All right, so now if I want to look at when the time constant t is equal to Rc, so then and for t I plug in Rc, so 1 multiple of Rc, just R over C, R times C over R times C, I get e to the negative 1, and then if I plug that in my calculator I get 0.37, so that's 37%. And then I multiply 0.37 times 9, so that's e to the negative 1 would be here, and I get 0.37, and I multiply it times 9, and I get 3.3 volts. So that's where this point comes from. And now if I do the same thing, if I say my t is equal to 2 times Rc, then I can cancel out my Rc's here, and I get e to the negative 2. When I plug that into my calculator, I get 0.14. Then if I multiply 0.14, this would be this value, 0.14 times 9, I get 1.2 volts. So that's why I'm down here at 1.2. And then I can do the same thing for 3. And so the way this is often used is I might be given a value for the resistance. Let's say resistance is equal to 1,000 ohms, and the capacitance is equal to, say, 1 microfarad. So my time, let's say I want to know what the time is to be at 37% of my maximum value. So to be at 37%, I need e to the negative 1. And so for e to the negative 1, that means my t is going to equal R times C. And I can find the time is 1,000 ohms times 1 times 10 to the minus 6 farads. And I can solve that, and t would equal 1 millisecond. And so that means that in 1 millisecond, this capacitor is going to discharge 63% of its voltage. So I'm going to lose that much voltage in the first in the first 1 millisecond. So that's the other thing. Like I can also I can also solve for something else. If I'm given a time and I'm given an R, then I can solve for C. Or if I'm given a C and given a time, I can solve for R. So that's how you would go about using this kind of if you were given this kind of a problem, how you would use the equation to solve for your variable.